Fatto.
Ottimo. Allora, so let's start. So I will share my screen. Good. So, okay, so last lecture, we have introduced the basics of quantum statistical mechanics. And we have seen that essentially quantum statistical mechanics is the same as classical statistical mechanics, with the understanding that where before we had an integration over phase space, now we have a summation over all possible quantum numbers, and we should substitute in the exponentials instead of the Hamiltonian, we will have the eigenenergies, and so on and so forth. Things are relatively simple. Now, let us see what are the implications, the new things physically that quantum mechanics brings in statistical mechanics. So now the first thing is the third law of thermodynamics. Now, last time, at the beginning of this course, we introduced the third law of thermodynamics, and we said that the third law of thermodynamics is important because it gives us a reference point to compute the entropy. And it's the statement is that the entropy at zero temperature should be equal to zero. Now, when we introduced classical statistical mechanics, strictly speaking, there is no way to see why this statement is correct there. So let me show you how it emerges in a simple way in quantum mechanics. And let me do so by solving a very simple exercise. I'm sure that you all know that a quantum harmonic oscillator can be, the Hamiltonian of a quantum harmonic oscillator can be written up in this form, right? If I assume that h bar is equal to 1. Have you ever seen this?
Yes.
Yes, excellent.
Yes.
And in particular, the raising and lowering operators are defined by the fact that the action of A on the vacuum is this, so it's essentially annihilating the vacuum, and the eigenstates of the quantum harmonic oscillator can be constructed by applying A dagger, the creation operator, n times, normalizing by square root of n factorial, everything on the vacuum, okay? And these states are such that if I take an action, the action of H on n, well, this is equal to omega times n plus 1/2 n. So these are the eigenenergies of my system, epsilon n. Okay? So now, since we are able to diagonalize the Hamiltonian, which is always the first step. I mean, whenever you want to compute a partition function or whatever in quantum statistical mechanics, you should always first diagonalize your Hamiltonian. Now, once you have your Hamiltonian in diagonal form, then it's trivial to compute the partition, the canonical partition function. This is equal to the trace of e to the minus beta h. And this can be written as sum over n e to the minus beta h n. And it's straightforwardly equal to sum over n e to the minus beta omega n plus 1/2. In other words, I can write it as e to the minus beta omega divided by 2 times the sum over n of e to the minus beta omega to the power n. And this sum runs from 0 all the way to plus infinity. Now, this is equal to what? What is it equal to? What is this sum that you see here? How is it called?
Power series.
Well, it's not really a power series. It has a
Okay.
much more, yes.
I'm sorry.
What is it? What is it equal to?
So 1 over 1 minus, sorry.
1 minus?
1 plus e to the minus.
Oh, no, 1 minus. 1 minus, yeah. Correct.
Okay.
So it's equal to this. Why? Why? Because this sum is a special case of what? What is this? Where r is smaller than 1.
It's a geometric series, sorry.
It's a geometric series, exactly. So, and this is always equal to 1 over 1 minus r. Okay, so this is the result for our partition function. It's a very simple and interesting result. So now that we have this for the partition function, we can easily compute physical quantities. So let us play the usual exercise that we have been playing many times by now. Let us compute the free energy. So the partition function, first thing you do is you compute the free energy, which is minus 1 over beta log of z, and is going to be equal to omega over 2 plus 1 over beta, the log of 1 minus e to the minus beta omega. Then we can compute the average energy. And simply doing what I've been doing many times in this course, right? Just a beta log of z. And well, if you do this calculation, you will get omega over 2 plus omega times 1 over e to the beta omega minus 1. Now, if you remember, what is the average energy, right? Remember that the energy is omega is the average of omega times n plus 1/2, right? So the average energy is omega times the average n plus 1/2. So this has to be equal to this. And therefore, this formula implies that the average occupation of my harmonic oscillator modes, the average excitation number, is equal to 1 over e to the beta omega minus 1. Okay? Now that we have this, what do? We take limits, right, to see whether this is correct or not. So what happens when the temperature goes to 0? What do you expect when the temperature goes to 0? What should happen when the temperature goes to 0? Hello? Are you still there?
Yes.
So what happens when the temperature goes to 0?
From the expression is omega over 2.
From the expression, the average energy is omega over 2. Now, is it consistent with what you expect physically? What do you expect physically when the temperature goes to 0?
Yes, it's h bar omega over 2, so it's omega.
Yeah, but okay, but what do you expect physically when the temperature goes to 0?
It's the ground state.
The system should be in the ground state. And what is the ground state energy? Is omega over 2. H bar is equal to 1.
Yes.
Right? And therefore, everything is consistent. Now let's take a temperature much larger than omega. And then you see that the average energy is equal to what? Is omega over 2 plus omega times. Now, if I expand, if the temperature is much larger than 1, this means that beta omega is much smaller than 1. And therefore, I can expand the exponential. We'll get 1 over 1 plus beta omega minus 1. So I get omega over 2 plus omega times kBt over omega. So this kBt over omega is actually the average occupation of my harmonic oscillator modes when the temperature is much larger than the frequency. Now I can take this, simplify, and I get that this is roughly kBt. So the average energy is roughly kBt. But this is true only at large temperatures, at high temperatures, right? Now, notice one thing that is important to keep in mind. In classical mechanics, classically, what would be the average energy of an harmonic oscillator? Let me repeat the question. Suppose that I give you the Hamiltonian H equal to p squared over 2 plus x squared over 2. I set all units equal to 1 for simplicity. We know that it doesn't matter. Put a 2m and a k here if you like. What is the average H in classical mechanics? In a microcanonical ensemble, let's say. What would be the average H?
I think kx squared over 2. But not sure.
What kx squared over 2? What, I don't understand your answer.
Yeah, I mean, I mean the average Hamiltonian would be I think yeah, I'm not sure. I should think carefully.
I think it's
You ever heard
equipartition theorem.
equipartition theorem? And what does the equipartition theorem tell us?
Oh yeah, it should be like 3 3/2 kBt. So depending, yeah.
No. This is a one-dimensional oscillator.
So it should be 1/2 kBt.
Why 1/2? No. It's not the prefactor is important. For this Hamiltonian, what would be the average energy? Do you have your notes with you?
Yes, I do.
Okay,
I
go
check
and
it.
look. What would be the average energy for this Hamiltonian?
It's KBT because
It's KBT, exactly. Why? Because for each quadratic term in the Hamiltonian, you get a contribution to the average that is KBT divided by 2. Guys, you will not pass the exam if you don't study, okay? So you should know the material. And this is something we have done centuries ago. Anyway, so it's KBT divided by 2, right? So each quadratic term contributes to the average at KBT divided by 2. Now, since here I have 2 quadratic terms, then the average energy is going to be always equal to KBT, always. Classically, this is always true. Okay? You see that in quantum mechanics, this is not true, always. It's true only in one limit, the limit in which the temperature is much, much larger than the frequency of your oscillator. Why? Because what happens when the temperature is much larger than the frequency of the oscillator? What happens is that the average occupation number of your mode, of your harmonic oscillator is very large. Is KBT over omega, is much larger than 1. And now I hope you know that an harmonic oscillator is in the semi-classical or classical limit when its average occupation is actually much larger than 1. Right? Did you know this? That the classical limit of the harmonic oscillator is the limit in which are the eigenstates in which the average occupation is much larger than 1. Well, if you didn't know it, I'm telling you. So in other words, the equipartition theorem quantum mechanically is not valid. It's valid only classically. Quantum mechanically, in general, is not valid. And in addition to this, we have that it is valid approximately in the limit in which the temperature is much larger than the frequency. Okay? So we already saw by doing a simple calculation that we have been performing 3,000 times in this class, we already saw one interesting thing, that the average energy is not given by the equipartition theorem quantum mechanically. Okay? Are there questions?
Can you repeat the explanation, please?
Which explanation?
About the limit of t greater than omega.
Well, in the limit of t greater than omega, you see, here I would have 1 over e to the beta omega minus 1. When t is much larger than omega, then beta omega is much smaller than 1. Therefore, I can expand the exponential and I get this. And then if you simplify, you get that the average n is equal to kBt over omega, and then you simplify everything and you get a kBt, right? But this is true only in the limit in which temperature is much, much larger than omega. Only in this limit it's correct. And now, in this limit, if you think for a second, the harmonic oscillator is in its classical limit. Why? Because the average principal quantum number is much larger than 1, right? And when the average quantum number is much larger than 1, the eigenstates are essentially classical. I mean, the dynamics is practically classical and the eigenstates look classical, everything is classical. Is the semi-classical limit. Okay? All right, so let us now compute something else. Let us compute the entropy. Now, the entropy is given by the derivative with respect to temperature of the free energy. And therefore, I will get minus log of 1 minus e to the minus beta omega plus omega over t 1 over e to the beta omega minus 1. Okay? Now, what happens when the temperature is much smaller than the frequency, omega? So in other words, in the limit which beta omega is much larger than 1.
The entropy becomes 0.
The entropy goes to 0, exactly, because this log of 1 is 0. And then here, if beta omega is much larger than 1, the limit of this stuff is 0. Entropy S goes to 0. You see, what we just discovered is that for this system, the entropy, as the temperature goes to 0, is actually tending to 0. This is consistent with what we stated many times, that being as the third principle of thermodynamics. Where does it come from? Well, it comes from the fact that in the quantum mechanical context, the entropy is nothing but K Boltzmann times the log of the number of states that are sitting in a certain microcanonical shell. Now, at 0 temperature, the microcanonical shell is essentially centered around the ground state energy. And if the ground state is not degenerate, and if the system is gapped, then it's straightforward. So if you have a gap in the spectrum, then it's straightforward to see that in practice, you will have that your entropy tends to 0. For non-gapped systems, you have to think a bit, but it's typically also true if you have non-degenerate ground states. Now, in the opposite limit, temperature much larger than omega, which means beta omega much smaller than 1, what happens? What happens is that your entropy becomes log of, so you expand all the exponentials, so you get log of beta omega plus 1. Well, then the log is dominating everything. So it's log of t over omega, roughly. And this is practically the log of the average occupation number of your harmonic oscillator, right? Because the average n is kBt over omega. Well, here I should have a kb. So in this limit, I get something that is consistent with with the third principle of thermodynamics, and in the opposite limit, I get that essentially the number of states can be estimated by looking at the average occupation of your harmonic oscillator. Okay? So this is an interesting exercise. By the way, one can do it, one can generalize it to...
Sorry.
Yes?
I thought that the expectation value of n is just t over omega.
Well, because you see, the expectation value of n is, I'm setting, sometimes I'm setting kb equal 1, sometimes I'm not setting kb equal 1. You see, okay. Look at this formula. Average n is 1 over e to the beta omega divided by 2, and beta is equal to 1 over kbt. Okay? Now, if you expand for beta omega much smaller than 1, you will get that average n is kbt divided by omega.
Oh, yeah, I see.
Okay?
Yes.
Then everything is fine. Okay, so do you have questions about this? By the way, you can easily generalize this problem to two-dimensional harmonic oscillators, three-dimensional harmonic oscillators, or whatever you want. I am going to actually, since we are close, we are almost getting to the end of the course, and you probably need to practice by doing some exercises, and we will do something in class. I mean, you know, usually when I was teaching in person, physically in a class, I would do at the end 2 or 3 lectures of only exercises to practice for the exam. Now, the problem this year is that I don't know how to do that because, you know, for me, if I cannot see what you're doing, it's a waste of time. Because if I would be present physically in the room, I can see what you're doing and I can help you improving. But if I cannot see what you're doing, it's a waste of time, right? Because I cannot help you. So, and I think it's practically impossible to do a tutorial of this type by teaching online. So what I'm going to do is I'm going to send you probably today through Patrizia, the text of a number of previous exams that we did you know, previously in the last 4 or 5 years. And I invite you to do those problems and to study the material, because I noticed by asking you questions that you're not very familiar with everything we have done. You probably studied for some other exams. I understand that. But if you don't know the material, then it's going to be very hard to be able to do the exercises. Anyway, I'm going to send you a number of exercises and suggestions for other exercises that you might want to do. And I invite you to practice. Now, concerning the exercises that I will send you, the ones of previous exams, if you want to ask me questions while you do them, or you have some doubts, well, you can send me a picture of what you have done and I can help you out. And I will be here available also during Christmas vacation. So don't worry, send me a picture And if you get stuck somewhere, we can figure out how to do that. Concerning problem, yes?
Actually, I have a question, maybe, I don't know, or a suggestion. So I
Yes.
heard this from my colleague that actually in Zoom breakout room we can do stuff like actually writing it online and stuff. So we can actually do things similar in the Blackboard, but maybe it's not convenient.
So you mean that each one of you goes to the Blackboard?
I mean that this Zoom meeting has a feature called breakout room. Maybe if they provide it for us, and they in the breakout room, I heard from my friend that we actually have something that we can actually write like you. So I don't know about that, but it's just a suggestion maybe.
Well, if there is if you would have a possibility to write like I do and share your screen, then, then everything can be done. The problem is that I'm not sure that each one of you has an iPad. You see what is the problem?
No, actually, I mean, the one that I'm saying to you is like someone who doesn't have an iPad, but they can actually do things like that in the breakout room. So I'm not sure.
But what is this breakout room?
Breakout room is like you divide the meeting into some groups, and yeah. So I haven't seen it myself, but I heard about
how do I? No, that's okay. But how do I see what you are doing?
You go into the breakout room.
Yeah, I go to the breakout room and then magically I see your paper.
No, of course. I think there are some features to do that. I don't really know about
That's
it.
what we should figure out, right? I mean, otherwise, if I cannot see physically what you're writing, then it's impossible for me to assess whether you're able to do an exercise and to help you out and to see how fast you are and so on and so forth. You see what is the problem? I cannot, if I'm not physically present, I cannot see what you're doing. Anyway, okay, let's go on now. So now that we understand what all these peculiarities of ideal gases, so the fact that, the peculiarities of quantum mechanics, the fact that the equipartition theorem is not valid, the fact that entropy goes to zero at zero temperature in accordance to the third principle of thermodynamics, let us go to the next fundamental topic of any statistical mechanics, which is ideal gases. And let us deal with quantum ideal gases. Now, ideal gases are made typically of indistinguishable particles, right? And they are essentially a gas made of molecules that are all the same. And they have a free Hamiltonian of this type. Now, if we put this system in a box of linear size L, then the eigenstates are going to be EP equal to P squared over 2M, where P squared is going to be a vector, where P is actually a vector Px, Py, Pz, and each one of them, P alpha, is equal to 2 pi over L times N alpha, where N alpha is an integer. Okay? So this is the spectrum of a free particle in a box. And I'm sure that with, here I'm assuming that I'm taking periodic boundary conditions, but you know, all of these are details. It's always more or less the same. You know that the moment you put your free particle in a constrained geometry, then essentially what happens is that you have to quantize the momentum in order to satisfy the boundary conditions. So if you put it with hardcore boundary conditions, you have to put boundary conditions to your wave functions to be equal to 0 at the two boundaries, at 0 and at L. Otherwise, you have to put periodic boundary conditions if you take your system defined on a three-dimensional torus. Okay, so all of this is standard stuff that you have done in quantum mechanics. And in particular, you all know that whenever you have a sum over P of something, of some function of the momenta, then you can always pass to the integral and write it as V over 2 pi cube integral dp of whatever. So let's keep all of this in mind for the future. So all of this is just a summary of something that you're supposed to know from quantum mechanics, which is just a diagonalization of a free particle in either with periodic boundary conditions or with hard wall boundary conditions, but in a three-dimensional geometry. So now the spectrum in general is going to be E equal to sum over P, epsilon P, and P. So epsilon P is just P squared over 2m. In other words, is px squared plus py squared plus pz squared over 2m. And NP is the occupation of the corresponding eigenstate of momentum P. Now, what happens is the following, that if you have quantum mechanical free particles, and you have a gas of many quantum mechanical free particles, then you all know that it's important to keep track of their indistinguishability. And in particular, indistinguishability determines the properties under exchange of coordinates of the wave functions. And you can distinguish among two broad classes of particles, fermions and bosons. Fermions are particles that have orbital wave functions that are symmetric under exchange of indices, while fermions are antisymmetric. And in particular, this implies, again, I'm telling you stuff that you are supposed to know from quantum mechanics. This implies that if you have a fermion, then you cannot put more than one fermion on a given level, on a given eigenstate. So a given eigenstate can be occupied by at most one fermion. So NP can be equal to 0 or 1 for fermions. Well, NP can be equal to whatever for bosons. Okay? So let's see now what is the consequence of this basic fact of life on the statistical mechanics of these particles? And in order to do so, let me compute the Gran canonical partition function, which is a function of chemical potential, volume, and temperature. All right, so the Gran canonical partition function, as you all know, is equal to the sum over n from 0 to plus infinity of little z to the power n, and then the canonical partition function of volume and temperature, where little z is e to the beta mu, is the fugacity. Now, Zn is something we already know what it is, right? Zn is equal to the sum over n of e to the minus beta en, or actually written up in a much better way for our system, is the sum over all possible strings of the occupation of all the momentum modes of our free system. So I'm telling you, for momentum P1, I have one particle. For momentum P2, I have 0. For momentum P3, I have whatever, and so on and so forth. That depends on whether I have bosons or fermions, but subject to the constraint that sum over P and P is equal to n. And then, if this is true, I will have e to the minus beta. The energy is going to be sum over P, epsilon P, and P. Okay? You agree with me, right?
Yes.
Okay. So then the Gran canonical partition function now is going to be equal to sum over n from 0 to plus infinity, sum over all possible strings n p such that sum over p and p is equal to n of what? Of z to the n, but z to the n, I can write it as e to the beta mu to the power n, and n is equal to sum over p and p, right? This is equal to n. And then e to the minus beta sum over p, epsilon p, and p. Therefore, this is equal to the sum for n from 0 to plus infinity, sum over np, sum over p and p equal to n of e to the minus beta sum over p, epsilon p minus mu and p. Now let's look carefully at this sum, at these two sums actually. So I'm summing exactly as what we have done. You remember, we had something very similar for the cluster expansion. Here we are summing over all possible number of particles, and then over all sequences of occupations subject to the constraint that the sum of all the elements is equal to n. Okay? These are the two constraints I have to satisfy. Now, I'm claiming that I can rewrite this as the sum over all possible sequences and p without any constraint. So I'm not requiring anymore that sum over P and P is equal to N of e to the minus beta sum over P epsilon P minus mu and P. I repeat, while here I get sequences with this constraint, since I'm summing over all possible N, this is equivalent of summing over all sequences without constraints.
It's a bit confusing me.
It's exactly the same thing we have done for the cluster expansion. So let me repeat. When you write sum over N and then sum over NP subject to the constraint that sum over P and P is equal to N, right? What you're saying is among all possible strings here of numbers, I'm selecting only the ones that satisfy this constraint. Okay. And summing over them. And then I'm summing over all possible values of the constraint. In other words, imagine that you take the set of all possible strings, NP, of all possible occupations. Then what you're doing there is the following. You're dividing this set into the ones, you're dividing the set of all possible occupations into the ones for which sum over NP is equal to 1, sum over NP is equal to 2, sum over NP is equal to whatever, N. Then you're performing the summation inside here, and then you're summing over all possible boxes, right? What I'm saying is you can perform this sum this way, or you can perform this sum by saying, okay, I'm just summing over all possible sequences, no matter what is the value of the constraint. So I'm essentially summing over all possible sequences that are sitting in the big box without partitioning it. Is it clear now?
Yes.
Okay. All right.
Professor.
Yes.
I have a request or maybe a question. Can you
Yes.
send us the notes that you've been writing? I mean, so
Can
we
I
can
do?
double check and stuff.
You can I do what?
Can you send the notes
Oh,
you're
that is going
writing?
to be a huge file. I thought you have essentially a recording of everything, right?
Yes.
I mean, I can do that, but I have to split it into. I mean, it's going to be. Let me see how big it is. Okay, just a second. Let me see how big is the file. It's 51 megabytes, so I cannot even send it to you. I mean, the file of all notes brought up to now, because it will bounce from the mail. So I can either split it and send it to Patrizia, and then Patrizia will send it to you, or you can just go back to I mean, if you have doubts, go back to the recording. I mean, everything is being recorded as far as I know.
Do you suggest us to watch also previous year's lecture?
Previous years. Well,
Yeah.
if you want, you will see many exercises. If you want, you should watch the last lectures of previous years, and you would see a number of exercises that we have done in class. The last 3 or 4 lectures, because typically I was doing exercises in the last lectures in preparation for the exam. So, but all the rest is the same. But this year, I mean, all the lectures this year are being recorded. Did you know that?
Yeah, I know.
Okay.
I mean, I was just checking because last time I didn't see updates.
Okay. All right. So then we can write the sum this way. Okay, now I have to retake it. Okay, so, and now this can be written as the sum over all possible sequences and P of the product over P of e to the minus beta epsilon P minus mu and P. Here I simply wrote this exponential of a sum as a product of exponentials. And this I can write as the product over P of the sum over NP of e to the minus beta epsilon P minus mu NP. Okay? Now I have to perform this sum, and the value depends on whether I have fermions or bosons. Why? Because if I have fermions, then this is equal to the sum over NP equal to 0 or 1, e to the minus beta epsilon P minus mu NP, and then this is equal to 1 plus e to the minus beta epsilon P minus mu. This is for fermions. For bosons, this is equal to the sum over NP that can vary between 0 and plus infinity of e to the minus beta epsilon P minus mu NP. And this is equal to 1 minus e to the minus beta epsilon P minus mu to the power minus 1, because it's a geometric series. Okay? Therefore, using this formula, we discover finally that our Gran canonical partition function is equal to the product over P of 1 plus e to the minus beta epsilon P minus mu for fermions, and it is equal to the product over P of 1 minus e to the minus beta epsilon P minus mu to the minus 1 for bosons. All right. Now, let's see what is the implication of this. And in order to see what is the implication, let me compute the average number of particles, which is 1, as we already know, 1 over beta derivative with respect to the chemical potential of the log of Z. And if you do the calculation, you will see that this is sum over P, 1 over e to the beta epsilon P minus 1 plus and minus 1. Now, this I can see it as the sum over P of the average occupation of each mode with momentum P, which tells us that NP, N average P, is equal to 1 over e to the beta epsilon P minus mu plus 1 for fermions, and 1 over e to the beta epsilon P minus mu minus 1 for bosons. So this is the one above is known as the Fermi Dirac distribution, and the one below is known as the Bose Einstein distribution. Okay. Now, let us now see how these distributions.
Wait.
Yes.
Can you go back to the previous slide? Yeah, previous.
Yes. Which one? This one? This slide or the previous one? Hello?
Yes, yes, thank you.
Okay. So let's now see how these distributions look like. Let us start with the Fermi Dirac. So the Fermi Dirac distribution is 1 over e to the beta epsilon P minus mu plus 1. So let's plot it as a function of epsilon P. I will have a certain, well, a value mu that is special. When epsilon P is equal to mu, this is equal to 1/2. And now what I see is that when epsilon P is much larger than mu, so on this side here, then actually this function, when epsilon P minus mu times beta is much larger than 1, is roughly e to the minus beta epsilon P minus mu. So it tends to 0 exponentially on this side. Well, when epsilon P minus mu is actually much smaller is actually negative. So tends to minus infinity. If you want on this side here, it tends to 1, right? Because this exponential goes to 0, and what I'm left is 1. So I will have something that tends to 1, is 1 up to a certain point, and then it is behaving this way, and then eventually is going to 0 exponentially fast on this side. So it's important to keep in mind that here it's exponential of minus beta epsilon p minus mu. Now the scale here,
Sorry, Professor.
yes,
When did you get a half, or what did you say to get a half?
well, put epsilon p equal to mu. What is this function equal to when epsilon p is equal to mu?
Exponential of 0, okay.
Yes, it's equal to 1.
Mm.
So now you see that the typical scale on which this function is varying, I mean, the scale around mu for which is neither equal to 0 nor equal to 1, the scale here is essentially set by kBt, right? So the smaller or the larger kBt, the more this function will have sharp or smooth features around the chemical potential. In particular, in the limit in which the temperature goes to 0, you have the so-called Fermi step distribution, which looks like this. It's equal all the way to the chemical potential, and then it's 0 above. So all states below the chemical potential are occupied, and all states above the chemical potential are empty at 0 temperature. Okay?
Sorry.
Yes?
Yeah, what I find really interesting with this function is the fact that at half, it doesn't really depend on the temperature, I think. So we only considered E equals to the chemical potential, but we made no reference whether this will occurs either at 0 temperature or when 0 temperature goes to infinity. I don't know if you could say something. Is it correct that at exactly half, we don't care about the temperature? This future is always going to.
No, it is certainly correct. The problem is that it's not a very important feature. So it is certainly correct, but it's not a crucial feature. And the reason is actually very simple. So the fact that it's equal to 1/2 there tells you that, okay, if you end up having picking up a mode that has exactly that energy is occupied by, it has equal probability to be occupied or empty, essentially. I mean, an occupation equal to 1/2, it means that you have equal probability of having something there or not having something there.
Regardless of temperature.
Regardless of temperature. But that is because that guy is sitting exactly on the Fermi surface, on the surface. I mean, okay, look, I didn't talk about what is a Fermi surface, but yeah, so it's a special point, right? I mean, all the states that are below, all the energies that are below the chemical potential have essentially more probability to be occupied than empty. All the ones that are above have more probability to be empty than occupied. And the one that is sitting exactly there has equal probability to be empty or occupied, essentially. Okay? So it's a special point. You're right. It's a quite interesting special point. It doesn't have much consequences physically, but it's a quite interesting special point. I agree. Are there other questions? Okay, so this particular form of the Fermi distribution is actually crucial in, for example, in solid state physics, right? I don't know if you have already taken a course on solid state physics or not, but you might know that. So how do we explain the difference between a conductor and an insulator and a band insulator in modern physics? And it's essentially a combination of the theory of bands, which is just a diagonalization of a space periodic Hamiltonian, and of the fact that we know that electrons are the carriers of charge conductivity in solids, and electrons are actually distributed according to the Fermi-Dirac distribution. So whenever, for example, you have a band insulator, it means that you have a you have a band in your spectrum, like this one, and for some reason, so like this one, and for some reason, the chemical potential is actually sitting here. So the band is completely filled. Each state in the band is filled by one electron. And when each state is filled by one electron, you cannot have conductivity. Okay, anyway, I would have to give you a course on solid state physics in order to explain this. It's not my task, so let's forget about this. And let me now move to the Bose Einstein distribution.
Professor?
Yes?
Actually, what was that you, I mean, what did you just explain? Is it about semiconductor or something?
No, I just explained you the difference between an insulator and a conductor.
Oh,
An insulator, a band insulator is when you have, you know that in solids you have bands, right? For electrons in solids, the spectrum is made out of bands. So if the chemical potential is sitting within a band, then you have a conductor. If the chemical potential is sitting it's sitting outside and the band is completely empty or completely filled, you have an insulator. So that's what I explained. But in order to explain this in detail, you have to take a solid state course that probably you will take next semester. I hope. I don't know.
I mean, is this related to
I think we have taken it already. So.
So then you have taken it already. Then it's excellent. You know this.
Sorry. I mean, is this related to the? I mean, since we are discussing the distribution of Fermi-Dirac, is this related to like the carrier distribution that they usually? Carrier distribution or whatsoever they usually discuss in solid states.
Yeah, well, you know, electrons, which are the carriers, are fermions. So they are distributed according to the Fermi-Dirac distribution. Okay?
Okay.
Now, Bose Einstein. Well, the Bose Einstein distribution is completely different. First of all, it is 1 over e to the beta epsilon p minus mu minus 1. Now you see that from this expression that epsilon p minus mu cannot be negative. Otherwise, I get a negative occupation and it doesn't make any sense. So epsilon p minus mu has to be positive. And the fact that this has to be positive means that if I have epsilon p equal to p squared over 2m, then the chemical potential has to be smaller, at most equal to 0. Cannot be otherwise. Because if it would be positive, then for a certain range of energies, you would get a negative occupation, which doesn't make any sense. So the chemical potential, unlike for fermions, the chemical potential of a bosons has to be negative, or it has to be below a band, below the band edge in general. Okay? And then once we decide this, then what happens is that in general, this distribution will start from e to the minus beta mu. So we'll start from here and then go down exponentially. Eventually here will look like e to the minus beta epsilon p minus mu, as usual, at large, for large epsilon p. Right? But mu is always sitting here. Mu is always negative. Now, there are a couple of important things to notice. One thing is that these two distributions look pretty much the same, okay, when epsilon p minus mu times beta is much larger than 1, then n Fermi Dirac is roughly n Bose Einstein, which is roughly n Gibbs, and this is equal to e to the minus beta epsilon p minus mu, right? So at energies that are well above the chemical potential on a scale set by the temperature, then, well, all the differences between these three distributions are practically irrelevant.
Sorry.
Yes?
What is Gibbs distribution?
Well, the Gibbs distribution is up to a normalization e to the minus beta epsilon p minus mu.
Is that different from Boltzmann distribution?
Yeah, it's Gibbs-Boltzmann. It's okay. I mean, Boltzmann.
Oh, okay.
It's fine. I call it, I mean, as long as it's an exponential, call it the way you want. Call it the Silva distribution. It's okay. All right, so now, this is the first fact of life. Second important thing, next time we will be discussing, actually probably next time in 2 lectures, so on Wednesday, we will be discussing what happens for bosonic systems when we look at the chemical potential as a function of temperature. The chemical potential, I said, is negative. But then, as you decrease the temperature, what happens to the chemical potential is that in many instances, the chemical potential as a function of temperature is negative, 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 and then it hits 0 at some critical temperature and stays 0 afterwards because it cannot be positive. So this critical temperature at which it becomes 0 is called the Bose Einstein condensation. Temperature. So, well,
Sorry, Professor.
yes.
Maybe I just ask this. Why do you say it can never be positive?
Well, what happens to this function? So epsilon p is a positive number, right? What
Yes.
happens to this function if mu is positive?
Will be negative.
It's going to be negative for, if mu is positive, then for all epsilon p that are between mu and 0, it's negative. It is negative. But this function is the distribution of particles, is the number of particles in a certain mode. Do you think a negative number of particles in a certain mode has a physical meaning?
No.
No, and therefore mu has to be negative.
Okay.
Or at most 0. Cannot be positive. Okay?
Yes, thank you.
I was saying when it hits 0, then this is called the Bose Einstein condensation temperature. Is actually a very interesting phenomenon. We will be discussing it in detail. And it's interesting because, well, it's not only important physically, but actually it took a long time to observe it experimentally. It was observed only when I was a student, so early 2000s. Last years of last century. So it's a very interesting subject. All right, so I think I'm done for today, for this lecture. So do you have any further questions? Okay, so if you don't have questions, then we meet next time on Monday. Let me see at what time, because I don't remember. On Monday. I know. We don't. No, we don't meet on Monday. We meet on Wednesday.
Yes, sir.
Yes, not on Monday. Okay, good.
Yeah.
Okay, so let's see you on Wednesday then. Okay?
No, I
Okay.
think we meet on
Okay.
Monday.
We meet on Monday, we don't? Do we? I don't know.
At 9, I think.
At 9.
Yeah.
But we should anticipate your the questions.
My what?
You said you sent us some questions to work.
No, I'm not sending you questions that you should do by Monday. I'm going to send you some exercises to be, and you should do them over the Christmas vacation.
Oh, okay, I see.
Okay.
Yes,
Okay.
Professor.
Yes.
So I just checked the weekly schedule, and we have class on Monday.
Okay, at what time? At 9?
Yes,
At
9.
9.
Okay, good. Then I'll see you on Monday at 9.
Okay. Thank you.
Okay, bye-bye, guys. Bye-bye.
Bye.
Bye.
Bye-bye.